let's say we're trying to integrate 1 over 1 plus x squared from minus infinity to infinity. So I've got two infinities. This is sort of like a doubly improper integral. Do I have to take two separate limits as the upper limit goes to infinity and the lower limit goes to infinity? In general, the answer is yes. Now, you might argue maybe we don't need to worry about that here because this is an even function. In fact, its graph looks like a bell-shaped curve. It looks like a normal distribution. It's not, just looks like one. So you might argue because it's an even function by symmetry, I could just do the integral from 0 to infinity, see if that converges, and if it does, double it to find this one. But in general, the integrand function is not going to be an even function. So in general, what you want to do is you want to split this up really into two separate integrals from 0 to infinity and from minus infinity to 0. Now, technically speaking, what I'm writing here is not the best style because in writing this, I'm implicitly assuming these are going to converge. Assuming convergence. In general, if you don't know whether they're going to converge or not, you should not do this. You can maybe be a little bit more relaxed at first when you're first learning this stuff and go ahead and write that anyway. But technically speaking, what I'm writing there is based on the assumption that they converge. They do converge, so it is a valid assumption, but I really need to prove that. How do I prove that? Well, let's take them one at a time. This one is a limit as b goes to infinity of the integral from 0 to b of 1 over 1 plus x squared. Use the fundamental theorem of calculus. That's the limit as b goes to infinity of inverse tangent, right? Integral of 1 over 1 plus x squared is inverse tangent or arctangent. Plug in the numbers. Inverse tangent of b minus inverse tangent of 0. Now, inverse tangent of 0, you can double check with your calculator, is 0. So this simplifies even further to the limit as b goes to infinity of the inverse tangent of b. Does that limit exist? You got to know something about inverse tangent. Pre-calculus knowledge is important. If you have no idea whether this limit exists, I mean, you could use your calculator and graph the function. Technically speaking, the graph could be misleading because the graph of some logarithms grows so slowly that it looks like they might have horizontal asymptotes, but they don't. So it could be misleading. And it could also not really fully inform you about what's going on. If you graph the ordinary tangent function from negative pi over 2 to positive pi over 2, it looks like this. Technically, over the entire real number line, it repeats. Continues looking like that over here and over here. It's a periodic function. Meaning it doesn't have an inverse function, but if we restrict the domain to being negative pi over 2 to positive pi over 2, where it's got vertical asymptotes, then it is a one-to-one function on that domain. It's got an inverse function, and the inverse function is the reflection across the line y equals x. Y equals x looks about like that. So the inverse function, the inverse tangent function looks about like this. That's the inverse tangent of x. And since the red graph, the tangent function has vertical asymptotes at plus or minus pi over 2, it flips. The inverse tangent has horizontal asymptotes at plus or minus pi over 2. If you didn't know that, and you're just relying on your calculator, you might just be guessing, oh, it seems like it has a horizontal asymptote at about 1.5 or maybe 1.6. But it's good to know the exact value of the horizontal asymptotes, pi over 2, which is closer to 1.57. And that does mean this limit is pi over 2. And ultimately, you can double that to say that not only this converges to pi over 2, but this converges to pi over 2 times 2, pi. But let's be a little bit more careful. Let's also think about the other one. if I have a minus infinity, technically, I got to let the lower limit of integration go to minus infinity. I need to write it as a limit like this. And then do similar kind of calculations as I just did. Get the inverse tangent of x evaluated from a to 0. But now, when I plug in 0 here, that's what gets plugged in first, and it gives me yes, a 0. This is still 0. So I'm left with the limit as a goes to minus infinity. I forgot my minus sign in here. Minus infinity of negative inverse tangent of a. In other words, I can bring the negative sign out in front and say negative limit as a goes to minus infinity of inverse tangent of a. But the answer's got to be a positive number if this limit exists, because this graph never goes below the horizontal axis. Well, two minus signs are going to make a plus sign. That limit, as you let the input for the inverse tangent go to minus infinity, is negative pi over 2, not positive pi over 2. So this becomes negative of negative pi over 2. That limit converges to pi over 2. And as you would hope, it makes logical sense. That means the original integral from minus infinity to infinity converges to the sum of these two integrals, pi over 2 plus pi over 2. It converges to pi. Amazing. A function that seemingly has nothing to do with circles has an integral equal to pi. Amazing, but true. Mathematica, can you confirm this for us? Integral from minus infinity to infinity of 1 over 1 plus x squared pi. How is this related to circles? It's a mystery. The mystery can be resolved if you use imaginary numbers. Why? Well, here's a hint. Plus or minus I makes the bottom of that fraction 0. I squared is -1. You'd be dividing by 0. In what's called the complex plane, this function, which has no vertical asymptotes when x is a real number, somehow has like vertical asymptotes when x is complex. You have a real axis going this way and an imaginary axis going like that. Yes, I am using my imagination. It's an imaginary axis. Plus or minus I are on that imaginary axis, and that's somehow where this function has some kind of vertical asymptote that you can't really imagine, because how would you imagine it? It's not clear.